Everybody. So I want to do an example here where we're going to use some of the methods we've been talking about in the last couple of videos to make a sketch of this graph, right? Which is really another way of saying to understand the behavior of the graph. To make a sketch means we know things like where it hits the axes, where its maximums and minimums are, what it does when it gets very, very large, those kinds of things, asymptotes, all that sort of stuff. So we're going to use all the methods we've been looking at to get there. So we're going to just kind of go through a process of collecting information. The function itself can give us information. And as we've seen, the first derivative can give us some information, and the second derivative can give us information about the shape of this graph. So we're going to take all three of those, the function, the derivative, and the second derivative, collect a bunch of information about the shape, and see if we can combine all that information to get a reasonable sketch. A very reasonable question to ask right now is, well, we know we have graphing software widely available to graph these things, right? Well, that's true, right? We're not graphing this because we don't know any other way to figure out what it looks like. But there are a number of reasons to go through an exercise like this. The couple that jump to mind are we're practicing using derivatives, which includes a lot of algebra, which is always good to practice. When we understand when we dig through things like this, we're going to create a better sense of intuition in ourselves, right? Intuition, in my experience, just means you've practiced a lot. If you're always having to jump to a computer, it can kind of disrupt the flow of thought. But if you can look at a function and quickly understand a bunch about it, you can start to make some intuitive leaps to what you should be doing with it, depending on the context of whatever you're working on. And then also, you can't always rely on a computer, right? There are functions out there that kind of break. Computers are just programmed by people to really approximate all these functions, and you can find ways to break that programming, sometimes on purpose, sometimes on not. And so if you don't have the ability to work with these functions without them, you might find yourself lost. And you might be in a position someday where you need to be the one to program it to do something with a function. So you need to understand this stuff. Okay, enough preamble. Let's get on with the show. So since I'm going to collect information from this, the derivative and the second derivative, I'm just going to start by finding those derivatives. They look like they're going to get a bit ugly. And so I just want to get that work out of the way. So I have the three. Once I have those three functions, it's a little bit more, it's a little less messy to just find all the information I want. So I'll start with the derivative of the function. All right, so it looks like we have a product rule. So we're going to need the derivative of x to the 1/3. Leaving this function alone. And then, of course, we'll leave x to the 1/3 alone and take the derivative of 3 minus x to the 2/3. Okay, so x to the 1/3, we use our power rule, 1/3 comes down, we get x to the negative 2/3, and we've got this factor of 3 minus x to the 2/3 plus x to the 1/3. The derivative here, we're going to have a chain rule. So the outer function is this 2/3 power. We use the power rule. So that 2/3 comes down. We subtract 1, we get negative 1/3. But then that inner function, 3 minus x, the function that we've been composing with, also has a derivative. That derivative is negative 1. So I'm just going to tack on a factor of negative 1. Okay, so there's the first derivative. However, we are going to be using this derivative to collect information. The way it's written right now is awful, right? This is an awful looking function. Plus, we're going to have to take the second derivative, and this thing is a mess, right? So I think it's worth our time to do a little bit of simplification. So I'm going to do a few things. I want to combine these two terms, and it's easier for me to think about combining them when we have fractions. So I'm going to rewrite those negative exponents as powers in the denominator. So this first term, we have our 3 minus x to the 2/3 in the numerator. I've got a 3 from that 1/3 and an x to the 2/3. Right? Then I've got this negative 1. I'm just going to bring that factor out front and make this subtraction. And I'm leaving a little bit of space because we're going to have to do some work with fractions, it looks like, with common denominators. So I want to leave space to multiply by common denominators. And again, I've got a fraction. I've got a 2 from the 2/3 and an x to the 1/3. both in the numerator. And in the denominator, I've got that 3 and a 3 minus x to the 1/3. Okay, so there's my another way to write down this same first derivative. So I want common denominators, and it looks like the common denominator, right? They both have 3s, so we're good on 3s. We need an x to the 2/3 and a 3 minus x to the 1/3. So I'm going to multiply this one here by 3 minus x to the 1/3 over 3 minus x to the 1/3. I'm multiplying it by 1, and I'll multiply this one by an x to the 2/3 over x to the 2/3. Okay. So what happens when we do that? Well, first of all, we get a common denominator. But notice in this first fraction in the numerator, 3 minus x to the 2/3 times 3 minus x to the 1/3, you add those exponents. We have the same base being raised to a power. You add them, that's 2/3 plus 1/3 is 1. So this 3 minus x to the 2/3 times 3 minus x ends up being 3 minus x. When we do this to the second fraction, x to the 2/3 times x to the 1/3, again, we add those powers in the numerator, and we get x to the power of 1, or just x. We've also got a 2 in front, so we're going to end up, and we've got this minus here, so we're going to end up with minus 2x. And then we've got our common denominator, x to the 2/3, 3 minus x to the 1/3. Okay, so already this is a ton simpler, and one more step we can take. We've really got 3 minus 3x. So let's factor out that 3. We'll have 1 minus x left in the top, and now we can cancel. I didn't need those parentheses, but it doesn't hurt. We can cancel these out, and now I've got a nice form that I'm pretty happy with. 1 minus x over x to the 2/3, 3 minus x to the 1/3. All right, I'm going to throw a little box around for myself. We're going to need this in just a few minutes. All right, right now I just wanted to get it. I know I'm going to use the derivative, so I just got the derivative. Okay. Again, where we started, right? This line up here, that's the derivative. But look at what we ended up with and how much simpler this is, right? This is going to be so much easier to work with. Remember the kinds of things we're going to be trying to find out. Where does this thing equal to 0, right? Try to think about how to make this top one equal to 0. Or where is it not exist? Or where is it positive? Where is it negative, right? How do you figure out where this is positive and negative going through all these different terms? We'll have a much easier time when we've got it in this form. So this is going to, even though it took some work to get there, this is going to be helpful for us. Okay, let's go to a new page because this is going to get ugly. So let's copy this derivative. We want the second derivative now, so it's just the derivative of this function. So let's just bring it down here and take the derivative of this function. Okay, so this one's going to get even messier. Looks like we've got a quotient rule. So f double prime of x, we're going to need to do the derivative of the top function, leaving the bottom, the denominator function alone, x to the 2/3, 3 minus x to the 1/3, minus 1 minus x times the derivative of the, oops, I forgot my power there, of the function in the denominator. And then we square the denominator. So we can multiply each power by 2. So this is going to be x to the 4/3, 3 minus x to the 2/3. Okay, now here things get awfully messy. I am not going to try to do this all at once. I want to do this a piece at a time to figure out all these little things going on. So I'm going to keep this half of the page just for doing some scratch work. So first, we've got the derivative of, so maybe I'll mark these things. We'll just use a red box. So first, I'm just going to write down what this red box becomes. So here's my little symbol. The red box becomes, well, the derivative of 1 minus x is just negative. So we've got negative x to the 2/3, 3 minus x to the 1/3, right? We left that second function alone. That one's not too bad. Now let's look at this piece of the puzzle, okay? So, in fact, let's look even less. Let's just look at the derivative of x to the 2/3 times 3 minus x to the 1/3. It's similar to the derivative we just took a minute ago, the first derivative, except the powers have switched, right? Remember, we started with x to the 1/3, 3 minus x to the 2/3. So it's going to be kind of a similar looking thing, and we're going to probably want to do the same kind of cleaning up that we did there, combining fractions and so on and so forth. So let's take this derivative. We've got our product rule. So the derivative of the first function is 2/3 x to the negative 1/3 times 3 minus x to the 1/3 plus x to the 2/3 times the derivative of this second function, which is 1/3, 3 minus x. Oops, sorry, there's something in my way. 3 minus x to the negative 2/3, and then we get a factor of -1. I'm going to play the same game and write these as fractions. So I've got 2, 3 minus x to the 1/3 over 3x to the 1/3 minus, that's our -1 at the end there, and I've got x to the 2/3, 3 times 3 minus x to the negative 2/3, so I put it in the denominator. We have the same almost common denominator, right? We've just swapped these powers of 1/3 and 2/3. So this first term, just like I did above, I'm going to multiply it by 3 minus x to the 2/3 over itself, multiplying it by 1. But when I do that in the numerator, that makes that 3 minus x to the 1/3 times 3 minus x to the 2/3 just becomes 3 minus x. So I've got 2 times 3 minus x from this numerator. This one, the second numerator will get multiplied by x to the 1/3, so we'll just get an x. And our common denominator is 3x to the 1/3, 3 minus x to the 2/3, which we can simplify. So notice what's happening in the numerator. I've got 6 minus 3x, which I could factor a 3 out of. And so I end up and cancel with the 3 in the denominator, similar to what we did last time, and I end up with 2 minus x, or x to the 1/3 times 3 minus x to the 2/3. Okay. Now that was just this back half of the blue box. When I combine that with that 1 minus x out front, I can just get a 1 minus x factor in the numerator. So I've got 1 minus x times 2 minus x all over x to the 1/3, 3 minus x to the 2/3. Okay. All right. Now we're getting somewhere. So let's look at the entire numerator now. The entire numerator is the red box minus the blue box. Okay, so now I'm going to have my red box was negative x to the 2/3, 3 minus x to the 1/3, and I'm subtracting 1 minus x over 2 minus x over x to the 1/3, 3 minus x to the 2/3. Okay, let's play a similar game and get a common denominator. So we don't have a denominator here, we do, it's 1. So the common denominator is this x to the 1/3, 3 minus x to the 2/3. So if we multiply the first term times that denominator over itself, notice what happens. We have an x to the 1/3 and an x to the 2/3. We get an x, got a negative out there, and we get a 3 minus x, and then we've got minus 1 minus x, 2 minus x, all over x to the 1/3, 3 minus x to the 2/3. Okay, we're running out of space here. We're just about there. This is our numerator. Let's do one more step on our numerator. Notice what we have up here. So I'm going to expand everything. I've got minus 3x plus x squared minus, let's expand these two binomials. I get 1 times 2 is 2. 1 times x is minus x, and then I'll get a minus 2x, so I've got a minus 3x, and then I get plus x squared over x to the 1/3, 3 minus x to the 2/3. There's some really nice stuff happening in that numerator, so I'm going to bring it back over here now. We haven't changed anything about the denominator, right? All we've been doing is work on the numerator. But notice what happens here. I've got a negative 3x here and a negative 3x here, but that second one is going to have this negative distributing to it. So it's going to become positive. So these two things are going to cancel. I've got a positive x squared and a positive x squared, but the negative is distributed. So those are canceled. All that's left is that negative 2. So that whole ugly mess boiled down to a negative 2. Oh, I forgot the denominator of the numerator, right? Sorry, we have a compound fraction. So that's the denominator that we left alone. Up here, we've got negative 2 over x to the 1/3, 3 minus x to the 2/3. Okay, last step, let's not have a compound fraction. This is ugly, so this is negative 2 over x to the 1/3 times 3 minus x to the 2/3 times 1 over x to the 4/3, 3 minus x to the 2/3. And finally, we can combine all those powers in the denominator. So our denominator looks like, we got x to the 1/3 and x to the 4/3. So x to the 5/3 and 3 minus x to the 4/3. And in the numerator, all we've got is a negative 2. And there is our second derivative, right? So not a short derivative to take, although I guess it was. We could have stopped at any point, but with a little work, we get something very, very, very simple. All right, so we've got our 3 derivatives. Let's now go back to where we were. Remember, all we wanted to do was collect information from them. So that getting the derivatives was kind of a separate project so that we could begin the work we really wanted to do. So now I've got my 3 functions. F of x is equal to x to the 1/3 times 3 minus x to the 2/3. F prime of x is equal to 1 minus x over x to the 2/3, 3 minus x to the 1/3. And then f double prime of x is equal to negative 2, what did we have? X to the 5/3 and 3 minus x to the 4/3. Okay, there we go. Yeah, that's what I have. There's our 3 functions. So let's get some information from each of them, okay? So from the derivative, or sorry, from the function itself, there's a few easy things we can get. Let's start with intercepts. Intercepts are always great. Intercepts. The vertical intercept, or the y-intercept, this is the place where x is equal to 0, f of 0. And in this case, putting in 0 for x gives me 0. It doesn't matter what happens to this term. We're already multiplying it by 0. It gives me 0. So the graph must go through the point 0, 0. What about the x intercepts? These are the places where f of x equals 0, right? We already found one of them at 0, 0. Is there any other place where x to the 1/3, 3 minus x to the 2/3 is equal to 0? Well, if we put in 3 for x, right, there's two factors. One of them has to be 0. Either x is 0 or 3 minus x is 0. The exponents don't change that. We need that base number to be 0 to be 0. So we get another place where this is 0. F of 3 is equal to 0. So we get another intercept of 3, 0. So let's just box these points we know our graph goes through. What else can we get from the function? How about where is it positive and where is it negative, right? So let's look at these two factors. Notice 3 minus x to the 2/3 is always going to be greater than or equal to 0, right? Because it's got that squared power in it. If you put a negative number to the 2/3 power, you're either taking the cube root, getting a negative number and then squaring it, or squaring it and taking the cube root. Either way, you end up with something positive. So that second term is always positive, which means the sign of f follows the sign of x to the 1/3. And so that's a very simple analysis. X to the 1/3 is positive if x is positive, and it's negative if x is negative. So that means f of x is greater than or equal to 0 if x is greater than or equal to 0. And f of x is less than 0 if x is less than, we can do less than or equal, it doesn't really matter. Just at those zeros, it's equal to 0 on both of them. But more importantly, if x is positive, f is positive. If x is negative, f is negative. And so that gives us some more good information about our function, right? We're just understanding what this function does. Finally, let's think about what happens as x gets really, really big or really, really small, right? So in other words, I'm asking as x, the way we can write this is as x goes to infinity. So we're putting in larger and larger numbers. What happens to f, right? Different kinds of things can happen. Some functions you've seen in pre-calculus have asymptotes, whereas x gets larger and larger, the function gets closer and closer to some number, right? Like y equals 7, it gets closer to that line. Sometimes they shoot off to positive infinity, sometimes they shoot off to negative infinity. So we want to start thinking about these ideas. Well, let's look at our function. If I put in larger and larger values for x, positive values, x to the 1/3 is getting really large, right? Taking that 1/3 root makes it smaller, but we're still getting large. The cube root of a billion is big. The cube root of a trillion is even bigger. The cube root of a trillion is even bigger, right? A similar thing happens here. If you put in a large number and you take 3 minus that large number, you get an incredibly large negative number. Then you take the cube root, you get a large, but not quite as large negative number, and you square it, you get a large positive number. So we've got two factors that are getting larger and larger and larger. The whole function is getting larger and larger and larger. So as x gets bigger, so does the function, and it does that forever. There's no end to how large this can become. The same thing happens in the opposite direction. The only difference is now the first factor is negative, the second factor is positive, right? As we're making x very large in the negative numbers, we're taking negative a billion to the 1/3 and getting a large negative number. 3 minus x is a very large positive number. And then it's got this 2/3 root, so it's still a large positive number. So we've got a very large negative number times a very large positive number, gives us larger and larger negative numbers. So what we mean by this is we can make f as large as we want in the negative direction by taking x as large as we want in the negative direction. I hate saying small because these are not small numbers. Negative a trillion isn't small. It's really large just in the negative direction. And okay, that is probably all the information we'll get out of the function for now. Maybe we'll think of something else and come back, but our intercepts, it's a good place to start. The sign of the function and this, what we call end behavior. All right, let's look at f prime now. The first thing we want to do is find critical numbers. Right? And this is, because we did all that work to put the derivative in this form, it's really easy to see the critical numbers. I'm not even going to write down any algebra. Critical numbers, remember, are where f prime of x equals 0 or f prime of x does not exist. And this is all just sitting right in front of us in this form of the derivative. F prime of x equals 0 if x equals 1, right? We need that numerator to equal 0. And as long as the denominator doesn't equal 0 at the same time, and you can see it doesn't if you put x in, you don't have to work out any of the numbers. You just see you get a 0 in the numerator and non-zero in the denominator. So the derivative is equal to 0 there. So we get x equals 1. We can also see that the derivative does not exist when we get zeros in the denominator. And those happen if x is equal to 0 or x is equal to 3, right? Again, that's easy enough to read right from what we have there, from that form, okay? So what we want to do with the first derivative is find out, let's start by finding out where is the function increasing and decreasing, which means where is the first derivative positive and negative. And so a good way to do this is to draw out a little number line with all the critical numbers on it. So we'll have the critical number 0, 1, and 3. And all I'm going to do is below in each of these intervals, I'm going to write down the sign of f prime, right? So we'll go through this piece by piece. Notice, so let's start below 0. X is below 0. So these are x values represented on this number line. So we're not thinking about 0. We already know the derivative doesn't exist there, but below 0, it does exist. What do we know? Well, let's look at our function. X to the 2/3 is always greater than or equal to 0, right? Same reason we talked about before, we're squaring something, okay? So we don't even have to think about what happens to that x, because it's always positive. So whether this thing is negative or positive depends on these other two factors, 1 minus x and 3 minus x. So if x is below 0, right, we're looking at this first interval here, below 0, 1 minus x is going to be positive. You're taking a number less than 1 and subtracting it from 1, you get a positive number. And then 3 minus x will also be positive. So everything is going to be positive. So the derivative itself must be positive. Okay. Now let's look at between 0 and 1, our next interval. Okay. So we're imagining any number between 0 and 1. Again, x to the 2/3 is always positive. I don't have to worry about it. 1 minus x, again, we're taking a number less than 1 and subtracting it from 1, we get a positive number. 3 minus x is a number less than 1 being subtracted from 3. It's going to be positive. Everything's positive. The whole thing turns out to be positive. Okay. Next interval is between 1 and 3. Now the numerator is negative. You're taking a number bigger than 1, subtracting it from 1, you get a negative number. In the denominator, we still get that x to the 2/3 positive, and 3 minus x is positive because our number is bigger than 1 but still smaller than 3. So 3 minus x is positive. We've got negative numerator, positive denominator. We have a negative number. Finally, our last interval, everything bigger than 3. Numerator is negative because we're subtracting a number bigger than 3 from 1. Denominator is negative because 3 minus something bigger than 3 is negative. X to the 2/3 is positive. So we've got a negative over a negative. We're back to positive. So our function f prime, the derivative of our original function, which is itself a function. Let's say it this way. F prime of x is greater than 0 if x is less than 1 or x is greater than 3. Okay, and f prime of x is less than or equal to 0 if x is between 1 and 3. I guess these are strictly, I don't need the or, it doesn't make it wrong, but I don't need these or equal to's here. What we know from this, we know a few things. F of x is increasing on, so let's see, it's increasing from negative infinity to 0. And then the union was 0 to 1. And then also 3 to infinity. Okay. We don't quite know what's happening at these critical numbers. We'll talk about this in just a second. And then f of x is decreasing on the interval 1 to 3, right? So these are intervals here. So it's decreasing on that one interval, increasing everywhere else, right? So more good information about our function. We can also look at the first derivative test at our critical numbers. Notice our critical number 1, we go from positive to negative. So there is a local max at x equals 1, right? We're going from positive to negative, right? So it's going up and then down. And since it's a local max, I'm going to go ahead and evaluate it, or at least approximate it, because ultimately I want to be able to draw this graph. So f of 1 is, so I'm going back to my original function. I put in 1, and you get, well, let's just write it out. 1 to the 1/3 times 3 minus 1, 2 to the 2/3. What is that? So 2 to the 2/3. 2 squared is 4, the cube root of 3. Well, we know it's between 1 and 2. Let's say 1.5, right? 1.5, 1.5 squared is 2.25 times 1.5 is pretty close to 4. So it's going to be a little bit bigger than 1.5. I just want to get an approximation. So we know the 0.1, 1.5 is part of our, or approximately 1, 1.5. And then we've also got a local min at x equals 3, where our derivative goes from negative to positive. It's decreasing and then increasing, right? And so we have a local minimum there. This is one of those critical points where the derivative doesn't exist. So we think maybe there's a corner there, something like that. But in any event, the first derivative test tells us there's a local min at x equals 3. And we already know that point. That was one of our intercepts, is 3, 0. So let's box the most important information, where my function is increasing, and then these local max and local mins, right? When we're sketching this, we're going to want to know that stuff. We're going to want to be very aware of that stuff. Okay, we're almost there. Let's finish up. With all the information we can get from the second derivative. So from the second derivative, we're going to get concavity, whereas a concave up and concave down, right? Telling us whether the shapes look like this or like this, right? Little pieces of these kind of up curves and down curves. So what I'm going to do is I'm going to look at the places, right? So we kind of did the same thing with the first derivative. Let me say it more explicitly here. When we did the first derivative, we looked for critical numbers, right? Places where the derivative is 0 or doesn't exist. One of the reasons those are such important places, besides being locations of max and mins, is a function. If our function is continuous everywhere else, everywhere everywhere that it exists, which this derivative is, then the places where it's equal to 0 or doesn't exist are the only places it can switch sign, right? If a function is continuous, right, it can't go from positive to negative without going through 0. So either we have a 0, or we have a place, maybe we have something like an asymptote where a function could be negative on one side of the asymptote and positive on the other, right? Those are the only two ways that a continuous function, well, one of them is discontinuous. You either have a discontinuity and it doesn't exist at a point to switch signs, or you travel through zero. That's another way to think about those critical numbers. So we're going to look for those same kinds of points with our second derivative. So where is f prime of x equal to 0? And where does f, sorry, double prime of x, where does it not exist? Well, the only way it's equal to 0 is if the numerator is 0 and the numerator is just -2. So this thing's never 0. So we don't have any numbers where this is true. But we do have several numbers where it doesn't exist. We can just see them. X equals 0 and x equals 3, right? That would make our denominator 0 and the thing doesn't exist. So that gives us something like critical numbers. I'm going to do the same game. I'm going to put out 0 and 3 on a number line and just see what the sign of my second derivative is. This one's really simple because we've got this 3 minus x to the 4/3 power. That's always going to be positive, right? Same reason that the 2/3 powers were before. The negative in the numerator is always going to be negative. So everything about this, the sign of this thing has to do with x. And we're going to be the opposite of the sign of x, because if x is positive, we've got a negative numerator and a negative and a positive factor next to x. So we have a negative over positive is negative, and if x is negative, we have a negative over negative is positive. So this is really simple to do. When x is below 0, we're positive. When x is above 0, in these other two regions, we're negative. Okay, so there is the signs of the second derivative, positive, negative, negative on these intervals. So this means we are concave up f of x in particular, not f double prime. Remember, this is information about the function from the second derivative. F of x has concave up from -infinity to 0. And f of x is concave down from 0 to 3 and 3 to infinity, right? So it's not concave up or down at 3. Something weird is happening there. The second derivative doesn't exist, so it doesn't really have concavity defined. We'll see more when we sketch this, what might be going on there. Notice a couple of things. We're concave down at x equals 1. The second derivative test tells us that x is a local max, and it just confirms what we got from the first derivative test. We can't use the second derivative test at 3 because we don't have concavity there, and our first derivative doesn't exist there, so the second derivative test doesn't work there. So it just confirmed what we got already from the first derivative test, but it's nice to see that they do agree with each other. Okay. We also notice that concavity switches as we go through x equals 0, right? And so x equals 0 is, well, let's put the point in. At x equals 0, the function, remember, we found evaluated to 0. That was up here. So at 0, 0, we have an inflection point. All right, so we've got some information from our second derivative. Okay, so ton of work, right? We did all this derivative work in the beginning, but I want us to notice a couple of things, right? Because there's so much to do, organization is going to be key, right? I knew I wanted the derivatives. I didn't want to have to do this derivative work in the middle of thinking about all the other stuff. Get the derivatives done, right? And in this case, they took a lot of work. But at the end, we've got three functions to examine. And then we just take them one at a time and figure out what information we can get from each. From our function itself, we can get intercepts. We can see where it's positive and negative, and we can try to decide what happens out at infinity and negative infinity. We can't always do all of these things, right? But these are some of the things we can do. From the first derivative, We can find out where it's increasing and decreasing. We can look for local maxes and local mins if the first derivative test applies. And then from the second derivative test, we can get concavity and inflection points. So let's see if we can now combine all this into a graph. So throw out some axes. Okay, so first thing I'm going to do, we've got the points 0, 0, and 3, 0. So I'm going to go ahead and put those in just to give me something. 0, 0, and 3, 0. We know that f is positive, right? So now I'm looking at this information. F is positive to the right. One thing I should say too is x is continuous, right? These are both continuous functions, and we have the product of continuous functions. So it's going to be continuous. So there's no jumps or breaks in it. So just to signify that it's positive to the right, what I know for sure, and it doesn't equal 0 anywhere else. We know these are the only two zeros. Whatever my function does, it must start out going up over here, and it must be going down over here, right? I might have to adjust that shape a little bit, but I know that happens. The other thing that I know happens is somehow or other at 3, it hits 0 and goes back up. So I'm not going to draw anything quite yet, but I'm going to think about that later. The other thing I might do right now to help myself understand is notice that as x goes to positive infinity, the function's going off to positive infinity. So I'm just drawing a little symbol to myself that that's what's going to happen. And I until I get more pieces in there, I don't know exactly where the function's going to be, but I'm just letting myself know that out at the endpoints, it does that, right? It looks a bit like that. Okay, so what next? Let's look at our increasing. So f of x is increasing from negative infinity to 0, and it is concave up. So I'm looking right here, I've got increasing from negative infinity to 0 and concave up, right? So concave up, remember, is something like this, or at least it's a piece of something like this. Only this half of it is increasing. So my function must be doing something like that. Concave up, increasing. Maybe now I'll erase this little extra line I had in there. Right, but that matched with what I thought it should look like. So there's my concave up, increasing section of the graph. Let's look at the next little section. Oh, I forgot to put in a point. Let's put in a point right now. Sorry, we had a local max at 1, 1.5. So somewhere, here's 1, and this was just an approximation. We had a local max right there. So I know my function's going up to that, and then going down afterwards. And I know I'm concave down from 0 to 3. So concave down, remember, means something like this. So I'm going through that local max, concave down, something like this, right? I didn't do it perfectly, that looks a little better. What this also tells me is if I switch from concave up to concave down, my shape has to be something like this. It's like I'm almost going straight up for a second. In fact, I am. The derivative is, loosely speaking, the derivative is equal to infinity. That's a nonsense statement, but the graph gets perfectly vertical for a moment. So I'm going to try to make this more clear by redoing this drawing. Now that I have a better understanding of what's happening here, this is going to look more like this. Concave up and getting very steep right as we get to 0. And then switching at that inflection point to concave down. Now we've got, and then we've got this, we're concave down and decreasing, right? Remember, we were decreasing from 1 to 3 and still concave down. We were concave down from 0 to 3. So we're concave down from 0 to 3, increasing until we hit 1. Remember, this is just an approximation, and then decreasing afterwards to 3. Now, what happens after 3? We are increasing again from 3 to infinity. So we're increasing from now on. And we're concave down. Concave down is like this. The only way we can be concave down and increasing is like this kind of the shape, this part of the shape. So what we've got here is a little corner. We know we hit this minimum here. That was one of our local minimums. And then we must do something like this. And there is a sketch of that graph. Right? It takes a while to be able to think through all of these different ideas at once and end up with these graphs, right? It's just going to take practice. Let's jump to a more sophisticated software than me drawing and see what this thing looks like. And there is a pretty, let's just look at them side by side for a second. Right, so we did okay, right? It's not exactly right, but we can see here's this local max 1.587. We said a little bigger than 1.5, so it's pretty good. And we've got this corner right, and the concavity looks correct. Let's look at this more nicely. And there's our function, right? My concavity was a little more exaggerated. You can see this thing almost looks like a straight line. A straight line will have concavity of 0. You can test that by taking the first and second derivative. This isn't quite a straight line out at the endpoints, but it's close to a straight line. You can imagine why that is if you think about the function. This will be the last comment I'll make. Remember, our function was f of x is equal to x to the 1/3, 3 minus x to the 2/3. If we're putting in numbers like a billion, right? If we're putting in numbers like a billion, this 3 doesn't really matter. So for large x, this is like x to the 1/3 times negative x to the 2/3, which is equal to x to the 1/3 x to the 2/3, because that's squaring. We're really pulling a -1 out and taking it to the 2/3 power, which is just 1, which is just equal to x. And so this graph starts to look very close to just the function x as you get larger and larger x. It's not equal to it, right? It's not equal to it. That 3 keeps it from ever being perfectly just the function f of x equals x. But for really large numbers, that 3 doesn't change very much, right? Try putting in a billion for x and taking x to the 1/3 times 3 minus a billion to the 1/3 times 3 minus a billion to the 2/3 is like just barely 999,999,999.9 or something like that, right? You can throw that in and see what happens. In fact, let's just do it right here. F of, see, even at 100, we're getting close to 100. At 1,000, we get really close to 1,000 as our output. This isn't big enough. So you can just see as I'm adding zeros, the outputs are becoming incredibly close to the inputs, right? Where at this point, the computer doesn't even notice the difference. The difference is so small relative to these numbers that it doesn't notice. So that's why this graph begins to look like this line. As we get further and further away, they look very similar. Okay, I guess one last thing. I know I said last thing already, but let's just look at those derivatives we found just to see how ugly. Here's the first derivative with its asymptotes, its places where it's not defined at 0 and 3. And there's the second derivative, maybe is even messier, has also asymptotes at 0 and 3 and does some strange things. But we've said enough in this one. Let's stop there. Thanks, everybody. I will see you next time.